John Mackay.
Thank you very much, and thank you for the organisers for the invitation. It's great to see some familiar faces as well here. So what I'm going to talk about this morning is something called Poincaré profiles, which built on something called separation profiles that were introduced by Benjamin Schramm and Timar, and then with David Hume and Roman Tessera we extended this to different measures of connectivity of an infinite graph. So I'll start by summarising some results there about how to measure how connected an infinite graph is. And then, particularly thinking about the hyperbolic case, go on to discuss variants introduced first by Pierre Clemenceau, called conformal dimension of the boundary at infinity, this some kind of fractal dimension, and then hopefully start to connect them. There's still many things to be completely figured out, but start to explore how these two apparently different ideas are connected to each other. So as I said, so this is talking hopefully by the end about joint work with David Hume, but also building a lot on previous joint work with David and Roman Tessera. So let's start by measures of connectivity of graphs. Perhaps it's easiest to think about Benjamin Schramm Timar's definition first. So if you have a finite graph, a very natural thing to measure how connected it is how hard is it to chop it into pieces at most half the size. So that's the cut size for a finite graph. The minimum number of vertices you have to delete. So that all components of gamma minus s have size at most size of gamma, number of vertices of gamma, divided by 2. All graphs today are going to be bounded degree. So think subsets of Cayley graphs or Cayley graphs as they come up with them. Okay, so that's the cut size of a graph. If you have an infinite graph, well, or finite, it's interesting for infinite. The separation profile is a function which looks for the hardest to cut subgraph of each size. Okay. So that's the separation profile, it's a function. And well, to get going, if we have, say, a 3 regular tree, then it's easy to cut any subgraph just using a single vertex in the middle. If you have separation of z squared, a moment's thought will probably convince you the hardest to cut thing should be something like a ball or a square, and you need square root of the area of the square to cut it. Or if we jump straight to ZD using a hyperplane, 1 minus 1 over d. It's not, there's 2 statements here being made, right? One is that if you have a particular subgraph, a box, is quite hard to cut. This hard to cut. And the other is there's no, any other subgraph you find might be easier to cut, but it can't be worse than that. So you have an arbitrary statement about cutting arbitrary graphs in at least as good a way as this, and a statement about for some particular subgraphs this is hard. Okay. And maybe one more, which intrigues as when we were starting this. So if you look at Hn, so hyperbolic plane, again, hard to cut thing be a disk, where the cut size will be logarithmic in the area, but once you get bigger, you have power behavior coming from cutting a smaller dimensional hyperbolic disk through. So this is in Benjamin Schramm-Timar, although this particular result builds on work about cut separators going back to the 90s with Thurston, Vavavis, a couple of other authors.
Sorry, HN is not a graph. You're taking what that is?
Good question. So let's make this make sense. And think for the moment just co-compact lattice, but in 2 seconds it will make sense. So people have been interested in cutting things up in computer science since the 70s, long before Benjamin Schramm-Timar kind of packaged it together into this invariant, which behaves nicely for groups. So maybe one other example worth mentioning would be Lipton, Tarzan, 79. So if G is a planar graph, then the separation, of course I didn't say that this way, is at most square root. So Thurston and co-authors in the 90s were interested in cutting graphs that weren't necessarily planar, but embedded into some nice space like a hyperbolic space. Okay, another motivation for them was being interested in embedding problems, including for planar graphs. The notion of embedding we'll have for now is a regular map. So a function between graphs is regular in the sense of Benjamin Schramm if it's Lipschitz and bounded to 1. So think of it sending the vertices to vertices, and we want it to be bounded to 1. Okay. Examples would be quasi-isometric embeddings, for example, or coarse embeddings even. You don't really care about distortion for this problem. And so, again, Benjamin Schramm-Timar, if you have a regular map between two graphs, then the separation of one is bounded by the separation of the other. Because if you embed your graph using this regular map, you can cut subgraphs in the image and pull that back to give subgraphs in X of roughly comparable size. When I write this squiggles today, I'm meaning bounded by multiplicative and additive constants. Okay. All right. And this implies in particular that if you have regular maps going both ways, like with a quasi-isometry, then the separation profiles are comparable. So if you have some some space like this, which you can pick a bounded degree graph that's quasi-isometric to it, then the separation profile of that graph you can take as the definition of the separation profile of this space, and it's going to be well defined up to squeal. Okay, other questions? Okay, so other measures of connectivity. So here we've used cut size and separation profiles. We can also use Poincaré constants, which are related to the Poincaré inequalities in the previous talk. So let me define those. This is from work with David and Roman. It's published in 20. So if we have a finite graph, then you can define the P Poincaré constant of that graph. Optimistic in my forward dividing there. By looking at the infimum of the norm of a gradient of a function divided by the norm of the function itself. So we'll take the p norms, f minus its average p norm, where f is a function on this finite graph to r, and non-constant, so we're not dividing by 0. And this here is the average. So let's think about this for a minute. If you have a lower bound for this constant that says for all functions this ratio is at least that constant, that is to say the gradient is bounded below by constant times this difference. Flipping that around, it says that how much a function varies from its average is bounded above by some function of its gradient. If your space is very well connected, if your function is going to change a lot, there's going to be lots of ways to get from one place to another, which will force the gradient to be big in lots of places. If your space is disconnected, right, at the other extreme, it can be different in different places and there's no way to get between them. There's nowhere you can make the gradient constant. So it's constant on the different pieces. If it just is connected to a very narrow pinch point, you can make your function just change in this very small place, but somehow still have a lot of different values. So this constant here is a Poincaré constant.
Can you clarify what you mean by the LP norm of the gradient?
Again, because we only care about comparable, you've got choices. The simplest would be to think of this now defined on the edges as the difference of values from the two vertices, and take the p norm.
You're thinking about bounded degree graphs.
All graphs today are bounded degrees, so
Okay.
exactly.
Sorry, I didn't understand what is f gamma?
F gamma is just the average of this function. So really, all my functions are on vertices,
Yeah.
and then you can, if you like, think of the gradient of f on the edges. And the average would be 1 over the number of vertices in gamma. So it's just the average. Yeah. You could assume the graph at average, the function was 0 average, but if you do that, at least to me, it's kind of conceals the fact a bit that you're really measuring the variation of the function away from its average. Okay, so this is something. And if you've got this finite graphs, you can see what is the most well-connected subgraph of each size in this sense. So that's these Poincaré profiles that we define this way. I'll normalize by the size of gamma, which will be motivated by the next remark. So up to normalizing by the size, what you're wanting to say is that what's the most connected subgraph of each size in terms of this Poincaré constant? We still have these same remarks if you have a regular map. I did not write regular, sorry. So if you have a regular map from x to y, then each of these profiles is going to be bounded above. Again, you pull back functions from the image to the domain. Okay. And it's well-defined QI invariance. To motivate where we're going, let's do the same examples. When the world of polynomial growth, things don't change. Oh, well, the remark to justify the normalization. It's mostly just David's work. If you do this with p equals 1, you get the separation profile. Okay. So this is a generalization of the previous thing, not an entirely brand new guy. When you're measuring one norms of functions, you can do it in terms of level sets, and you get harvest. Okay. So for example, if you do ZD for these profiles, turns out you always get the 1 over 1 minus d. You get the same growth of Poincaré constants. This is not unrelated to the fact that it's a classical thing to prove Poincaré inequalities on groups of polynomial growth, and for balls in groups of polynomial growth, that you can use that to get one of these directions. On the other hand, even just for the tree, things start to look a bit different. As p varies, these constants start to grow. There is some diffusion in the tree, which separation, it was enough to just delete a point, but you can spread out the changes a bit as p grows. So then, if we start to think about Hn, well, if I draw these exponents, for Hn, for different p, we know that Hn contains r n minus 1s. So our separation profile is going to be above this line, the first example. Hn also contains trees, so it's going to be above this line, which crosses at n minus 1. And it turns out that's basically it. What you have is r to the 1 minus 1 over n minus 1 when p is less than n minus 1. You have r to the 1 minus 1 over p when p is bigger than n minus 1. And when p equals n minus 1, no longer does the Euclidean space suffice, but you need to an annulus or a ball, and you get an extra log factor coming in from the radius of that ball. So it's slightly above there's more going on than just the power at that point. And of course this generalizes the previous result of Benjamin Schramm-Timar, and you see why there's this apparently different behavior going on. It's due to the fact that H2, the biggest Euclidean, the spheres look like R1, and so you're getting this log factor coming from the middle term, whereas for separation, p equals 1, it already suffices to just consider the spheres. Okay. This is a prototype of the result that we actually proved, where n minus 1 is the dimension of the boundary. So dimension, when you've got Hn, the boundary is an n minus 1 sphere, and there's different ways to talk about dimension, and all of the interesting ones are n minus 1. But we've got different hyperbolic groups, there are different ways to talk about what boundary we've got here. And to say what that is, we'll have to go on and talk about conformal dimension. But this thing here looks like something interesting is happening. Okay. So let's call that a critical exponent. That sounds dramatic enough. So let's call it critical exponent for Poincaré profiles. Be the infemal value of p, so that the p Poincaré profile is at most r to the 1 minus 1 over p. Some remarks about this. Well, clearly by definition, if you have a regular map from x to y, then this thing is less, for x is less or equal to that for y. So we can use this to rule out embeddings. Less obvious, perhaps, is this set here. This set here is going to be an interval. It's going to either be empty or everything from 1 to infinity, or half open or half closed interval from the exponent up to infinity, and all those can arise.
So sorry, what? So the critical exponents is p. What's the subscript? Lambda?
Here, lambda, well, there's lots of critical exponents floating around, so we put lambda here just because it's coming from the Poincaré profiles. So what is this saying? For hyperbolic groups, for these profiles, if you know what a tree does, you know what the hyperbolic group, all the finite graphs do. And there's some point at which smaller things, p becomes small enough that things other than trees matter. And this is saying, what is that exponent? Not obvious would be, well, it's an interval basically by Holder's inequality and quick calculation. Other things worth saying, oh, if you have an embedded tree, you could have, instead of putting less than or equal to, you could have put comparable to. So if you're in the world of hyperbolic groups, it's perhaps most natural in that hyperbolic context where you have trees. And we're saying, when do more than trees matter? Okay, other questions? Right, so let's switch for a while to conformal dimension. Anything else I should say?
Do you need a group or it's just like a workspace?
Say again?
For the last line, do you need a group or it is just like a workspace?
You just need an embedded tree. Space would be fine. Well, one thing I didn't mention, we talked about expander graphs this morning. So separation, if you want to cut up a graph, you can just delete all of it. That's not very efficient, but it works. Separation is always at most linear. Likewise are these profiles. And for both of them, you're going to be little o of n if and only if you don't have an expander graph in you as a result of David's. So expander graphs, of course, being the most connected things, are where you are close to, you're comparable to linear in an infinite sequence of scales. Okay, so conformal dimension. Previous talks mentioned also some ingredients for this, like Alpher's regularity. So a metric space, Z, is Alpher's Q regular. This will be our notion of dimension for fractally like things. If there's some measure on the space, so that balls have measure comparable to the qth power of their radius. Okay, so Rn is n regular. Keep going with the von Koch snowflake. It's going to be log 4 over log 3 regular. So these don't have to be integers. It'll agree with the Hausdorff dimension, box counting dimension. These are nice, well-behaved fractals. If you have two metric spaces, and you have a homeomorphism between them. This is quasi-symmetric. Let's write QS, quasi-symmetric. If the shape of balls is roughly preserved. So if there's some uniform constant L, so that for all balls in Z, B gets sent to, well, some blob-like thing, because it's a homeomorphism. And if you look at the ratio of the in radius to the out radius of this blob, it should be bounded uniformly over all balls and all scales. So you preserve the shape of balls, but not necessarily their size. If you preserve sizes, like your bi-Lipschitz as we were hearing about before, then you are a quasi-symmetry, because with L is just square of your bi-Lipschitz constant. But you could be other things, like if you raise a metric to a power, you've dramatically changed the size of some balls, but you haven't changed their shape at all. So you could have L as 1. Example of this would be the line going to the von Koch snowflake up to bi-Lipschitzness. This is raising to a power less than 1. In particular, you see that dimension changes. If you're making a t-shirt or something, this is nicer, but for most mathematical purposes, this is nicer, right? We want to make things as smooth, as nice as possible. And that brings us to conformal dimension. This is a variation of Pierre's definition.
Sorry, what does QS stand for on the,
Say again?
what does QS stand for in your definition?
Quasi-symmetric. Really here I'm lying, but it's true for spaces we care about. This is weak quasi-symmetric. As introduced by Tukey and Weissler, I guess, from about 81. So this is true, for example, for quasi-conformal homeomorphisms of Rn. So, okay, so given a metric space Z, the conformal dimension is the infimum of the regularity the Q regularity of all spaces that are quasi-symmetric to it. Okay, so you've got some fractal, try and flatten it down as much as you can using quasi-symmetric maps, and then the value you get is the conformal dimension. This Q is always at least well, it is the Hausdorff dimension, which is always at least the topological dimension. So if you've got something pretty flat already, you can't go lower, like Rn or an n-sphere. But sometimes you can, like we just saw the von Koch snowflake. It's quasi-symmetric to the line, so its conformal dimension will be that of the line, Q1. We seem to have veered away from groups, so let's veer back towards groups. Recall if G is hyperbolic, then you have a boundary at infinity of G coming from all the rays that go to infinity, and the time when they split apart is the Gromov product of A and B with respect to some fixed base point. And a visual metric on the boundary is one where it's comparable to some power of the Gromov product. Okay. In particular, whichever visual metric you pick is going to vary by multiplicative and power behavior, so they're all going to be quasi-symmetric to each other. More generally, Pollen and then Poincaré. If you have hyperbolic groups, then the groups are quasi-isometric to each other if and only if their boundaries are quasi-symmetric to each other. So for hyperbolic groups, if you're interested in the quasi-isometry geometry of them, the coarse geometry, is exactly captured by this boundary behavior up to quasi-symmetric maps. Conformal dimension is clearly quasi-symmetric invariant, so the conformal dimension of the boundary of a hyperbolic group is a quasi-symmetric invariant of G. Okay. And it often captures more than just the topology of the boundary would. Just a few examples, and then we'll try and connect this back to their previous. Okay. Well, if we've got a free group, boundary infinity is a Cantor set, which has positive dimension, but you can anti-snowflake it. You can raise the metric to a power bigger than 1 to get this down as close as you like to 0. So it's 0, but not attained. And that's basically it for 0. You're either, you're virtually free. If we have a surface group, so we're looking at the boundary of H2, that's a circle, so we get 1, and it's attained. And by result of Bonk and Kleiner, this is the only thing that attains dimension 1 as virtually co-compact Fuchsian groups. There are other things that don't necessarily attain dimension 1. If you take the boundary infinity of this guy, so the boundary infinity of this will look like circles with lots of arcs coming off it. So this is bigger than 1. It turns out bigger than 1 for any deformation, but you can get as close as you like to 1. This was already an example of Pansu. And there's a result of mine with Matthias Carrasco. A couple of years ago, which says conformal dimension 1 things all look like this, assuming we're accessible. Let's just say no 2 torsion. The conformal dimension is 1 if you're built up by amalgamating finite and co-compact Fuchsian groups. Over finite and two-ended subgroups. So you can start gluing together surfaces and finite things, and you'll get all the things that have conformal dimension 1. Yes, thanks. So one direction goes back to result of mine from about 2010, where if you're not one of these, you've got some subgroup which has no local cut points in its boundary, and there's a result which said that is conformal dimension bigger than 1. And then what we did in this paper is go the other way, which says you glue together things of dimension 1, you stay dimension 1, as long as you're just gluing along cut pairs in the boundary. But there are other things in this out here, right? Well, maybe I should say how this is proved. Everything here has been kind of trivial. If you have a Q-regular space and you have a product with an interval, it turns out this conformal dimension is Q plus 1. Imagine if this was a Cantor set, that was dimension 0, this was dimension 1. But when you do the product, you get Q plus 1. So this again goes back to Pansu, it's also used by Bourdon, where if you wanted to make this smaller, you'd be wanting to push these lines together with each other. Because you're preserving shapes of balls, you'd be wanting to rip, you want to anti-snowflake the lines, and you can't do that without breaking connectivity. I don't know if that helps anyone at all. This is now how I remember my intuition for this. But you could just treat this as a black box. So if you've got a product structure with an interval, you have a way to bound conformal dimension from below and something beyond just the topology. So using ideas like this, for example, Bourdon, well, let's do Pansu first. If you have the conformal dimension of the boundary infinity of complex hyperbolic, let's say 2 space, so this is a 4-manifold whose boundary is a topological 3-sphere, but the topological 3-sphere is one of these, well, some sphericalization of a Heisenberg group that was mentioned before with the cardinal metric. And that guy has dimension 4, in particular, not 3. So you've got 3 spheres for boundary, topological 3 spheres, but the groups aren't quasi-isometric. Complex hyperbolic 4 space is not quasi-isometric to real hyperbolic 4 space. Even more dramatically, perhaps, Bourdon has a family of Fuchsian buildings where a couple of parameters, all the boundaries are topological Menger sponges. One of these fractals drill holes through a cube. But the conformal dimension of the boundary, it takes a dense set of values between 1 and infinity. Okay. So all these different dimensions of the boundary where it's the same topological boundary. And then earlier work of mine, and also in different models with Drutu, and then also built on by, improved by Delat and De La Salle and Oppenheim, and different models again. It says for random groups, you can often get this conformal dimension. Usually the boundary is Menger sponges, and you can get the conformal dimension going to infinity. And this is the only way I know, actually, in these groups to show even that they're not commensurable to each other, these random groups. You know they're not isomorphic because of Euler characteristic, but if you're trying to show anything even algebraically quite strong, the only way I know to do it is to use this quasi-isometry invariant and these kind of analytic arguments. In both these cases, roughly what you're doing is you're seeing some kind of family of curves in the boundary, which you use as an obstruction for the lower bound for conformal dimension. Okay. Sorry, I was planning on using one of these boards, not 2. I can see everyone's eyes, so I think I got away with it. Question?
You define this field, but you define direct product structure?
So for the random groups, I build what's called a round tree, basically, in Gromov's asymptotic invariance. I'm not sure, was it Gromov or was it...
Don't draw there.
Oh, sorry. I'll find it straight. I build a hyperbolic cone on a Cantor set cross interval, roughly. Bourdon, I guess you probably have those in there, but Bourdon and Pajot later shows, I mean, even stronger, they show a Poincaré inequality on the boundary. Maybe in Bourdon's first paper he uses just a family of curves. Have to look it up to check. The words I'm not saying that, and I will say, is modulus of curve families comes into it. Okay, so we've got our two characters here. We've got some measure of connectivity of graphs in terms of Poincaré inequalities, and some measure of dimension of boundary in terms of conformal dimension. And with David and Roman, this result here, these n-1s are the conformal dimension of the boundary of this guy. So I'll just write that down. Now it turns out that one direction of this result just uses conformal dimension, but the other uses something stronger about the boundaries. Boundaries of rank 1 symmetric spaces, boundaries of Bourdon buildings have these Poincaré inequalities. If you just assume that, which implies they attain their conformal dimension, if you just assume that they attain their conformal dimension, then by result of Bonk and Kleiner, that implies they have a Poincaré inequality on the boundary, a 1-cube Poincaré inequality, which by our estimates is enough to get that the profile has the same format as the real hyperbolic world, where when P is bigger than Q, what matters is just that you've got trees in there. When P is less than Q, the boundary geometry pushes in to give you geometry of the spheres in the graph, and the Poincaré inequality in the boundary gives you something on the Poincaré constants of those graphs. And then in between, you need to average the boundary over a big annuli to get a different, slightly stronger Poincaré inequality. Everything I just said was about lower bounds, right? Finding these things. The upper bounds work just using the conformal dimension. In this case, we have that this critical exponent is equal to the conformal dimension of the boundary. This implies if you have between such things a regular map, for example, if you have a subgroup which could be highly distorted, there's no boundary extension, but if the subgroup maps regularly, so if you have a subgroup, then it will be a regular map, or more weakly if you just have any old regular map of one group into another, then we know that the Poincaré exponents have this inequality, but if you have the equality with conformal dimension, you also get that.
Sorry, Q is the conformal dimension here?
Yes, thank you. Okay. So you can rule out groups embedding into, or spaces embedding into each other in a weak way, even highly distorted way, using these Poincaré profiles, where the the obstruction's coming from the geometry of the boundary, which isn't preserved by the map, if that makes sense. The question we have is whether this is always true. So it's true in the case that G has this attainment property. Well, H doesn't matter. Is it true for all hyperbolic G? That if you have a regular map from G into a hyperbolic group H, the conformal dimension has to go up. Okay. And what is the new steps in this direction with David is we're interested in cases where you don't have Poincaré inequalities in the boundary. And for groups, this gets a little bit fiddly to prove that no such thing exists. There's examples due to Bourdin and Pajot, but I think their geometry is still a bit mysterious. However, for spaces, it's quite straightforward. If you have, say, a snowflake or a cantor set across an interval, there's no Poincaré inequality there because there are no curves going in no rectifiable curves connecting the lines. But we know the conformal dimension exactly. So our theorem is, for these guys at least, we have the right critical exponents. If you look at the critical exponent for C cross I, well, C cross I is the boundary, so we better do some kind of hyperbolic cone. So take a hyperbolic space whose boundary is C cross I. Then that's the same as the conformal dimension of the boundary C cross. Oh, I won't do I, that's unnecessarily. Introducing notation, let's just do 0, 1, which is Q plus 1. Okay. So if you have this product structure in the boundary, then you have the right critical exponent on the nose. So how it's round trees again. So I'll try and draw a better picture here. So if you have, there's a picture a bit like this in asymptotic invariance. Think of a tree being kind of spun around. Anyway, it ends up in a cantor set cross interval in the boundary. The thing about these round trees is that, in some sense, they're quite easy to cut. I mean, they look a bit like trees from one point of view. You can just cut along this line here, and you'll disconnect the thing in half. So what you need to do, rather, is play a bit of a game where you're looking at trees rooted at branch points here of sort of median length, which are going out a certain amount of distance, and you play the factors against each other, and you can do that to show that if for any p strictly less than q plus 1, the Poincaré constants will grow strictly more than a tree would. And this applies basically when you've got round trees to say something. So for example, if you have...
What's a round tree is? What's a round tree?
So a round tree Gromov defines as, if you take H2 in a quasi-symmetrically and a quasi-convex tree with a base point on the at origin, and then you spin this H2 and H3 so that the tree sweeps out a two-dimensional subcomplex, he calls that a round tree. Yeah. It's a tree that's been swung around. Put it that way. So if you have, say, Heinze groups, where all the acting diagonally in an RD and all the guys are positive. Again, this is conformal dimensions was already in Pansu's 89 paper, then they have the same critical exponent for Poincaré profiles as their conformal dimension. So you get obstructions to embeddings between them. I should also remark, so this is for regular maps, but Pansu also has a different approach entirely using coarse conformal geometry, which also includes coarse embeddings, which can rule out such embeddings between groups like this and many, many others for a different big family of interesting maps. Also for random groups, say, you also get this, the estimates for conformal dimension agree with the estimates for Poincaré profiles, which are going to infinity linearly in the length. And the last thing I wanted to mention is for conformal dimension 1, where, as I said, when the boundary has no local cut points, conformal dimension is strictly bigger than 1. So using the round trees from that, we get that the separation profile grows at least like a power bigger than 1. Sorry, power bigger than 0. So the exponent is strictly bigger than 1. So qualitatively, if you have a group whose conformal dimension is bigger than 1, I don't know, 3, then there's some number beyond which you can't embed into a hyperbolic group of conformal dimension 1.01. The case, this result's been also obtained independently by Ben Said, Geneva, and Tessera. And a couple of years ago, the fact that this implies the conformal dimension has to, sorry, the separation profile can't be log was a result by Lacaze and Lazarevich. So now again, the power here is you need to get this being bigger than 1. So when it comes to the world of conformal dimension 0, we said was same as virtually free. And the separation profile is constant. Conformal dimension 1, we had this characterization which of when having no local cut points in the in some subgroup boundary. So we have that characterization giving you that the separation profile, and hence everything bigger than that is bigger than some power bigger than 0. Conformal dimension 1, though, I think is still pretty mysterious. I mentioned if it's attained, there's a nice algebraic characterization in terms of being virtually co-compact Fuchsian by Bonk and Kleiner. Of course, this is then using Casson-Younggreth's Tukia and this whole world. These guys have the separation profile is logarithmic because it's a hyperbolic plane. However, we have another result which says there's more than that. If you have this example I drew before, if you have, say, a one-ended hyperbolic group whose GSJ just has quadratically hanging pieces, these guys don't attain conformal dimension, but they still have logarithmic separation profiles. So the world of separation profiles, the smallest thing you can have apart from constant is logarithmic, and there's more than just virtually Fuchsian in there. There's also some, for example, if there are no rigid vertices, you get these guys in here. But we have some examples where there's some rigid free vertices, but exactly what the characterization is unknown. There are examples of conformal dimension 1 where it's not everything, by, again, Lacoste and Lazarevich. If you have, if you double a surface group over some filling curve, so you've got a rigid surface vertex here, then the separation profile is not log. And their argument, I think, would extend is bigger than a power bigger than, it's like log, bigger than log, I don't know, to the power 1.5 or 1.2 or something like that. So what we're seeing is conformal dimension 1, so these separation profiles could potentially give some, and related Poincaré profiles could give some finer information into the boundary behavior. This is maybe not a surprise. When the conformal dimension is attained, we expect a perfect structure in the boundary that we can understand quite well the group inside. When it's not attained, something's getting worse, and how fast or in what way it gets worse should presumably be reflected in the geometry in the inside of the space. So hopefully there's more to find that way. So questions remaining are, well, characterize what's log and what's not. And that question up there, monotonicity of conformal dimension for regular maps or coarse embeddings between hyperbolic groups. Thank you.
Other questions? So,
I have a question.
what about p less than 1? Oh, sorry.
I have a question. So sorry, I went in the blackboard on the top there. Can you repeat why? So you said you don't need that H attains a conformal dimension.
Okay, so the upper bound here, the fact that this is less than here, doesn't use that assumption of attaining conformal dimension. The lower bound uses the assumption.
Okay.
So if you're wanting to get a contradiction here, you need the lower bound on this and upper bound on this. So it doesn't matter if H attains or not. This is not unrelated to Hansu's approach, where he has two different kinds of dimension here, conformal dimension this side and an LP cohomology dimension on the. And that gave me an extra 30 seconds to decide I definitely don't have a good answer for p less than 1 either. Somehow things stop being convex. We're happy to go down to separation. That was our goal. When p goes to infinity, you can do that, but it basically just is a different way of talking about the growth of the group.
So what's the spectrum of conformal dimensions among hyperbolic groups?
So there's nothing between 0 and 1, and this is true even for metric spaces by, well, the definition I gave would be Tyson, but it's also true by, for Hausdorff dimension by a result of Kovalev. So if you got something less than 1, you can deform it down as close as you want to 0. Bigger than 1, there are countably many hyperbolic groups, so you just know that there's countably many values between 1 and infinity, and Bourdon already gives you density. You can use this to do some nice tricks with random groups, where you can look at groups where the number of relations grows polynomially, and if you pick the right polynomial growth rate to target a value which conformal dimension is not attained at, then you get infinitely many QI classes of random groups, even with slow-growing models.
Anything known about the Diophantine properties?
Not by me.
What sort of numbers?
Well, so Bourdon's number here is 1 plus log q minus 1. So something logarithm in the vertical branching and logarithmic arc cosh p minus 2 over 2 in the horizontal branching. So this is from right-angled polygons with at least 5 sides and branching at least q times. So if you give me any particular number that's not an integer and not this, whether a conformal dimension takes that value for a group boundary, I don't think anyone knows. Sorry for going 2 minutes and 7 seconds into lunchtime.
Let's thank John again.